Hey there, welcome back. Today we're going to be doing some streaming on a new community project that I want to start up, and I'm calling it YoshiBot because, well, I couldn't come up with any other name. The idea is we're going to be building a wheeled robot, a rover, and I want to do a few things with this project. First, I want it to be modular, so I want to do assemblies for all of the parts on it that allow us to, make it larger or smaller. So I'm thinking a 3-wheeled robot, a 4-wheeled, and a 6-wheeled. So some different configurations. I also am going to make this obviously all open source, so open hardware, open schematics. The 3D models will all be open software, everything. So anybody that wants to can go build one of these. Right now, it's just kind of a loose idea in my head of exactly what we're going to end up with. But I do want to kind of drive toward lower cost. I'm not going to go for, the absolute lowest cost, but we're going to go with lower cost, as low cost as you can get with larger components. So it's not going to be, a really small thing. I'm thinking probably 6-inch to 12-inch size, somewhere in that range, probably closer to the 12. Yeah, so that's pretty much the design requirements or design ideas. I do know that I want to end up building a custom PCB for this so that we can have a single PCB that is dedicated for this. Now, for prototyping, I'm going to start with the YoshiPi because I have it and it's convenient and easy to use. But obviously, this thing has more hardware than we're really going to need. I mean, most importantly, right, it's got a whole bunch of real estate taken up by a display, which we don't need. But I do want to use a Raspberry Pi Zero. I guess this is a Raspberry Pi 2 or 02W. The small form factor and small power requirements are what I'm after. I'm thinking we'll build maybe 1 or 2 PCBs that stack up. The size of this might be a bit large for what we want. Maybe we want something smaller, especially if we want a single PCB that can drive things like, just a 3-wheel vehicle as well as a 6. This is probably fine for a 6 footprint wise, but 3-wheel, that's probably a little bit large. The initial one, since we're trying to drive for low cost, will probably be an amalgamation, a collection, if you will, of other off-the-shelf stuff. A classic example is we're going to use servos. Now, I don't think I have one sitting on my desk. I've got some in the bins back here. I haven't even really looked to see which size I want to use, but just to give you an idea. So here's a motor for it, and in fact, let me change the camera for us. So here's a motor that we're going to be using. One of the wheels and tires, talk about that stuff in just a minute, but the idea is that for steering, and here's an assembled version here, right? So if we've got this, we're going to have a servo on here, and that servo will turn this entire assembly. We're not going to have, I guess like a rack and pinion or anything like that. Also not going to be doing wishbone suspension or anything. This is just going to be fixed mount suspension. But for steering, these are going to turn the whole thing, right? So that means that we're going to need servos to drive that. So in order to drive a servo, we need a PWM. Now, the Raspberry Pi does have PWMs, but I think we need more than it provides directly. And just for simplicity, I'm going to use something like this. So again, let's take a look at this real quick. So this is a PWM generator. If the camera will focus, come on. One thing I hate about this camera is it just does not like to focus. There we go. So this has a PWM generator, and we can bring power in here, and this will generate our PWM. Now the part on here, I think this whole board, I mean, I guess what I'm trying to say is something like this is very inexpensive because these are made by, you know, probably the thousands, right? So the question is, if we do a custom PCB, do we take these parts and roll them onto our own PCB? And I think the answer to that is going to be, at least for the initial one, maybe no. Instead of using, you know, the components from it, we might just have boards that we take something like this and it mounts directly onto it. I've also got, good question, where is my driver? So I've got a driver for the motors as well. Let's see if I can figure out, I'm going to need that early on here. There it is. So I've got this driver. Let's go back and look at that. So you can see we have this 8833. It's a DRV 8833 driver, and we're going to use this to drive the motor. Again, this takes PWMs in order to affect speed, but in order to build one of these, I doubt I can build something. I probably can't even buy the parts in low quantity for the price I can buy this fully assembled. So we might have a spot where this just solders directly down to the PCB. So that's just kind of a rough idea of what I'm going to be going toward. Now let's see, let's pull up. I've already created a repository, so let me pull that up on GitHub. All right, so you can see here, it's at .NET Maker's YoshiBot. So I've got a very, very rough README here that has a little bit of a schedule of some of the features that I'm thinking that I want to build, some descriptions of some of the platforms that at least right now I envision. And over here, I've got the bill of materials for at least the parts that I'm thinking that I'm going to end up using. Now, this is all very, very preliminary, very rough guesses on a lot of this. It'll undoubtedly change as we move forward. And again, right now, this is just me working on it. If anybody else has a desire to help out or work on this, do any of this kind of stuff, extend it. By all means, it'd be great to have help. The more people working on it, the faster it'll get done, but also the more representative of, a lot of different users we can be and have it, meet a lot of different needs. All right. So I guess that's, good enough for an introduction. I don't think we need to do a whole lot more. I'll go over to Discord real quick. Let everybody know that we are currently streaming. So give me 1 second while I make that happen. We'll see if that brings anybody into the chat, but at any rate, let's keep moving forward. So that kind of gives you, a brief overview. Might want to have more of a formal meeting setting up some of the kind of, goals of this. But for right now, since I'm the only one working on it, I don't really need to have a meeting. I'm just going to let you guys know where it is. You'll be able to track status of the project really at this repository as I move forward. If anything changes, we can change that as well. Also, worth noting, there's a channel over in the Discord for this. I guess I can bring that up if anybody is overly interested in that, though most of us know what Discord looks like. So if we come over here, you can see there is a YoshiBot channel. Right now it's got the link to the repo pinned. So that's another place to keep an eye on. So either Discord for questions, things like that, and the repository here. All right, so today I actually want to get a little bit of productive work done rather than just run my mouth about what it is that I'm going to build. So let's go over and take a look at some of this hardware that I had out. So here's a motor that I'm going to be using. Now this one is and this is probably one of the more important things if you're going to be following along. You don't have to match this exactly, but it will certainly help if you do. This is a 6 volt, 130 RPM motor. So it doesn't move really fast. And 6 volt is, I'm not 100% certain why I'm going with 6 volt. The reality is I'd talked to somebody else and he wants to build this too. And I think he had selected 6 volt. Now, it may have been because of his idea on batteries when I ordered these. Yeah, so this is the motor that I'm going to go with, right? It's actually pretty good size. This one has an encoder on it, so it's got some circuitry here that we can sense its rotational direction, speed, position, things like that. Initially, I don't see any reason that I'm going to implement that. Right now, I'm just going to worry about driving this. But if we've got this motor, the next thing we need is we need to obviously put a wheel and tire on it. This is a standard wheel and tire from, I think, probably Traxxas and things like that. The important thing on these when you're looking at them is this one's got a hex built into one side. This is the inside. So here's the outside. It's got a hex in it, and this is a 12 millimeter hex. So if you get a shaft coupler that has a 12 millimeter hex on one end, and it would be nice if it would focus. Really, there we go. So this hex fits down in here like that. And then you can run a screw in to hold it in. And then a set screw or grub screw goes in here. And this is a 4 millimeter shaft. So this goes on here, and you run that set screw down against the flat of that shaft. And once you've assembled all of that, you end up with one of these. So this is our drive assembly. Now, in order to run this assembly, we need 6 volt power again, as it said here. But what we want to do is our microcontroller can't output 6 volts directly, especially not at any kind of amperage. So we need a driver in order to move this. On this one, you can see I actually have soldered on these 2 pins. Basically, you've got 2 wires. And if you look at the data sheet, and I probably have one, I'll put it into the repository. The 2 outside ones are listed as motor positive and motor negative. The reality is they aren't necessarily positive and negative. It just they affect the direction of rotation. So if you swap the polarity of those, it'll reverse direction. In order to change the speed of this, since this is a DC motor, what we can do is we can change the voltage that comes in on this. And the easiest way to change voltage on DC is to not actually change voltage, but to use a PWM. So we basically go high to 6 volts and then low to 0, and the proportion or the duty cycle of that will give you a range of 0 to 6, which on average, which then will adjust our speed. The easiest way to do that is with a motor driver. So we're going to use this DRV 8833. I think this can do like 1.2 or 1.5 amps. I did look this up. I made sure that I sized them properly. So the amperage that this pulls maximum does not exceed this. This also can drive 2 motors at a time. So it's got, you can see, 4 outputs and 4 inputs. So the inputs, for example, on this, if we're going to drive one of these, you would hook 2 of the outputs to the input on this, so motor plus and minus. And then the inputs, you drive 1 high and 1 low, and that will change, run the direction. So if we have, say, in1 high and in2 low, it will rotate one direction. And if we swap that, so in1 is low and then in2 is high, it will rotate the other way. If both are low, then it stops. So this provides a real easy way to drive these at variable speeds and change its direction by feeding a PWM into this. So since we need to PWM into this, we're going to use a PWM driver. This uses I2C to communicate to it, so we really only need 2 wires, I guess 4 if you count power and ground, but 2 for communication from our microcontroller over to here. So we're going to use this. We'll have a couple of wires coming out wherever. The I2C will just pull off of this bus here maybe. We could pull off of the Grove. It doesn't really matter. I probably actually have some Grove wires that we can plug in here and then come over to here. That'll give us a PWM. Then we can drive this out to here and get our motor voltage in here. So this takes in, your logic voltage, which will be either 3.3 or 5 from this. And then our motor voltage, which will be up to 6 out to here. Now for power on this, initially I'm just going to use a bench supply. But in the final, what I want to do, and I thought about this a lot, originally I was going to put some batteries on board and then you could plug it in and recharge it. But then you have to have all the charging circuitry and a bunch of other stuff that honestly I just didn't want to deal with because, well, as engineers, being lazy is an asset. Often we're lazy because it's easier to do something else. So I figured I have a bunch of these. This is a Milwaukee M12 battery. You can buy, generic Chinese made, whatever. I guess this one's made in China anyway, but you can buy non-Milwaukee branded ones of these for cheaper. The nice thing here is you can see it's 12 volts, but it's 16 watt hours, and they make a few different sizes of these. The nice thing is it's got a pretty good amount of power in it, and you can then have a charger, get a bunch of these, and then I've got one of these. This is just an adapter, right, that it comes wired like this, so it's got a power switch, which may or may not end up on it. Seems kind of handy, and it's even got a fuse holder. But we can take this, and this mounts basically just like that. So that gives us a 12-volt battery input, and then we just move the charging off board to, a standard fast charger from Milwaukee. So you can easily swap out batteries and do that kind of work. So it's got a kind of a French cleat type mount here, and it actually comes with a mounting pad that may or may not end up being used, but that'll all be done in the 3D modeling when we get around to that. That's several weeks out. But this is what will end up powering things. We'll have to go through some sort of a regulator to bring it from 12 down to 5 for this and up to 6 for the motor. Maybe we'll only drive the motor at 5. That will limit our speed, so we won't be able to go as fast as the motor can, but it would simplify things for us not having to output 2 voltages from our power supply. Again, those are all decisions we can worry about in the future. For now, I am going to just work with the bench supply. So I've got a bench supply over here on the side. I can, I guess, when I edit this down and put it up on YouTube, I can put links to the power supply, but it's just a bench supply that we can give 5 volts to. All right, so first task for today will be to prove out this motor assembly, right? So what we want to do is we want to hook this up, verify that the wiring does what it's supposed to do. We can drive this forward and reverse. We can do that without even a microcontroller. We're just going to do that with some wires using our drive here. Once we have this drive and this working, showing that we can move it forward and back, then we're going to connect up the PWM generator and the YoshiPi and write a little bit of code to hopefully drive this wheel forward and back and adjust speed, do that kind of stuff. The goal today really would be to have a class for the assembly, at least a starting point for the class for this assembly that allows us to set the direction and speed of rotation of the tire. So I think that's probably a good point to start. All right. So I guess that's a good goal, and that's what we're going to drive toward. I also am going to point out that I am very new to live streaming. I've done a lot of video content creation, but not a lot of live streaming, so I will stumble and act like I don't know what the hell I'm doing, because generally speaking, I don't know what the hell I'm doing. All right, let's open up Visual Studio. I'm working on Windows. There's no reason you have to do that. You could be doing all of this on Linux, yada, yada. Let's change our camera to screen, and since I run dual monitors, Visual Studio always gets confused about this, which is baffling to me because a lot of developers do this, and you would have thought that that would have been one of the main test, I guess, environments that they'd use, but whatever. Okay, so let's start with, boy, it's already immediately, it's like, what do you start with, right? I think I'm going to start with a blank solution. And so you might wonder why I would go that route instead of selecting, like a YoshiPi app. And I know from doing lots and lots and lots and lots of IoT applications, literally I've done thousands of different apps. One of the things that we're going to want to be able to do is do simulation. Sometimes it's not convenient to have hardware. Sometimes it's a pain in the ass to have to hook everything up. Sometimes, you might be on an airplane and all you have is a laptop. You want to get a little bit of work done, whatever. So you want a simulation environment. That means that we need 2 different projects for this. We would need one for hardware and we would need one for desktop. I actually recommend doing that for almost any IoT project you're doing, because by forcing yourself to support multiple platforms, you force yourself to write better code every time. You will have much better code base if you force yourself into multiple platforms, because it forces you to do separation of concerns. So I'm going to start with a blank solution. Let's go ahead and put it out here. I think I've already cloned this. Yep, perfect. So we're going to put it in this folder, in the source folder, and we're going to just and hopefully it creates just the solution file without creating another directory for me. See? It opened it up on the other monitor yet again. Just the small things, Microsoft. It's just the small things. You could do so much better. Let's see, where are our properties window? I'm just going to open this up in File Explorer. I'm just opening it up to make sure that it put it in the root folder rather than down in a couple of folders, right? So this is exactly what I didn't want it to do. I want the solution to be in source. So I got to take all of this and move it every time. And there's no option to not do that. All right, so now we have it where we want it. Nope, couldn't possibly remember where the last folder I was. Could you? All right, ta-da. Now let's add a project to the solution. Now I'm going to create a class library first. This will be our core. So this is where common logic for all platforms will be. And the temptation is to just go with .NET 9. However, if I end up wanting to support the Meadow F7, maybe we want to, use a Meadow F7 feather on this. There's no reason we couldn't support that. In fact, I think I will, just because it's kind of interesting. The final solution on this, the final project that we build for this, might end up being a core compute module with the F7. I don't have one right at hands. There we go. So here's a project lab, but the core compute module with the F7 is this module here. And you can see that it's actually even smaller than the Pi 0. So that's an option. It would require surface mount, and not gonna lie, surface mount kind of scares me because I don't have a whole lot of equipment, especially don't have the experience for doing it. I do have a hot plate and I've done some surface mount stuff. In fact, the YoshiPi has a couple of surface mount components, got a couple of connectors that I actually put on before I ship. But, that's my experience for surface mount, is being able to put that quick connector on there. At any rate, what was I saying? Oh, yes, we're going to target, because we might want to use the Meadow, we're going to target .NET Standard with this core. It does not hurt to go with .NET Standard 2.1. We're not losing any functionalities or features because we're going to use a newer language version. So we're going to create that. Hello, Visual Studio. Create. What are you doing? Man, that took forever. Okay, so we've got our YoshiBot core. I'm going to just add 2 new projects right now as well. We're going to add the YoshiPi version. And we're going to add a YoshiPi desktop. Now, the desktop app is just a standard .NET console app. Really, the YoshiPi app, and yeah, let's just create this one first, and then I'll show you that the YoshiPi app, it really is just a desktop console app as well. It just added in a couple of NuGet packages and did a little bit of template work for us. So let's add this console app. We're going to call this YoshiPi or YoshiBot. desktop. We're going to go with .NET 9 on those. Create. Okay. So the desktop, you can see here, just an executable targeting .NET 9. And, you know, we could actually do language version. Let's do the latest. And the Yoshi Pi is an executable. In fact, actually, I'm going to leave this at .NET 8 simply because I think I still have .NET 8 installed as the runtime on this hardware, and I don't feel like upgrading it to .NET 9 right now. This could be .NET 9 if somebody has a burning reason that we have to go to 9 or a compelling argument, then I can do it. Otherwise, I'm just going to leave it at 8 for now. We can move it to 9 at some point when I feel like upgrading the runtime on the device. But the point being, the desktop, you can see, it's just a standard executable running a .NET version. We could do this to make them the same. I guess it doesn't really make a lot of difference. And this one here, same thing. And I'll set it to the latest as well. But you can see it added micro layout and Yoshi Pi, NuGet references, and you know, it built our application over here. But really we have, you know, a static task main here, and in our desktop we have our static main here. All right, I'm going to add project references over to core. And there we go. There's our initial project. And not surprisingly, everything builds. Ta-da! All right. I could check this in, but we'll check in at the end of the day, or at the end of the stream anyway. There really isn't a lot of code that has to happen, especially right now. For now, let's just try to get this thing to work. We want to get this hardware working. So let's come back here. We want to drive this with this. Just make sure that the wiring here is correct. And in fact, while I'm at this, let's go look at the data sheet, or what I have found for a data sheet. Where did I put that? Bring that over. So this, I believe, is correct. I'm not positive, but this is one that I found. So this looks a lot like the backside of this. We've got our Hall effect sensors for the stepper, or for the encoder, right? So that's all of this internal stuff, right? The 2 through 5. And you can see it's got motor plus and motor minus, though. It says M1 and M2 here. Really, again, it's not plus and minus. Don't think of it that direction, or as, don't think of it as this is, you know, plus and ground, or VCC and ground. Think of it as it's just the connections. It's the difference between them that gives you the speed and direction. So if we swap the voltage, it just rotates in the other direction. So if there's a difference, a potential difference between them of 0, we've got 0 motion up through the maximum the motor will take. 6 volts in this is full speed. So a potential difference between them of 6 volts is full speed, and the polarity of it is the direction. But all of that said, I'm rambling. All of that said, M1 and M2 are the outside pins on this, right? So all of the inside stuff is the encoder, which we're going to ignore. So I took the outside pins, blue and red, and I just soldered them onto a couple of pins like this. And the reason I did that is it's much easier to stab these in to something like a breadboard. So now I can stab that in here. So our power for our motor is connected. Let's try to move this camera up a little bit, give us a little bit better view of what we got going on here. Let's see. That's straight-ish. Okay. So we've got our breadboard and we're connected up to the motor. When we try to drive it, I'll tip it like this so that it runs, but it's not very stable that way. Okay. We have our driver here. So let's put this. We've got our outputs on this side, so I'm going to orient it this way just for simplicity. And let's orient it like this. And just, you know, my goal is for people who don't do a lot of hardware. So my goal with a lot of this is people who don't have any or very little experience with hardware but know C# can do stuff. So when I do things like placing this, automatically there's thought that goes into it that is probably important. You know, it's from experience. I put this way this direction, right? And the reason is that I know that this has some outputs that I can go from here to here. And in fact, I could just take this and plug it into the outputs over here. In fact, here, let's do that. But the reason that I have it so far this way is it gives me all of these holes, which will allow me to add inputs as well as wires to hook to like an oscilloscope or a sensor or things like that. So let's just plug these two in here. These are give us our outputs. Now, I really should just modify one of these wires. The temptation to depin or cut these wires is really high right now. I've got a whole bunch of them just to get them out of the way. In fact, you know, let's do that. Where are some cutters? I have the tools to depin these, but those are all the way across the office. I was hoping that I had some cutters just sitting right here. We'll just use these. And again, these are just for the encoder in theory. I'm just going to remove them. That way we've got less that we have to look at. Okay. So now we have to bring in some power. I do have a variable. Sorry. I do have a variable power supply over here off to my right, off camera. So here are a couple of wires that come from it. Now, in a perfect world, I'd have a connector on here, you know, kind of like this, that allows me to plug it in, but I don't. So I'm going to go with the, you know, the lazier way of doing this. And I'm going to grab a couple of pins. Sorry that this doesn't have much for visuals as I dig wires out. Trying to find something with colors that are somewhat power and ground related. So this is where we have our input power and ground. Here. And then I've got these wires here. These are called micro grabbers. These ones aren't super micro, but they're fairly small. So if I push here, you can see this little hook comes out. That allows me to easily hook a pin, right? So I can hook that. And I can hook this. And as long as those two don't touch, we're good. The other ends of these, I can then clip onto here to get power from that power supply. So when I don't have connectors, this is a typical way I'll do it. So that's how our power is coming in here. Just through these micro grabbers. Now these are fairly thin wires, but we don't have a whole lot of power that's required to make this happen. Okay, so that gives us our power here. Now just to make things a little bit cleaner and a little bit easier to see, I'm going to connect up. In fact, I'm going to do this instead. I'm going to bring the power and ground from the power supply to this rail here. And then we'll connect from here over in hopefully what is a little bit easier way to see for you guys. I'm hoping I can find some short wires. Let me grab those. So I have a kit of shorter wires that hopefully will make things a little bit cleaner, easier to see what I'm doing. So first we're going to connect the ground here to the ground. So the ground comes in on this to this row, and then from ground here to our ground. We'll do the same thing for the power. Of course, these are all way longer than they need to be, but whatever. Power. Here. All right. So we've got power and ground to it. This, I'll pull it back out. Now, oftentimes you would solder it with these pins facing down. I did this one, I soldered it together so that this is up, so that I can see this and I don't have to constantly refer to a data sheet. But it has an LED on it right here that shows that we have power. So if I put this back and make sure I align it properly. Which I did not. There we go. All right, so now if I power it up from the supply, we should get an LED here. So let me turn on the supply. And you can see we've got, yeah, there it is. So we have power. So we're successfully doing that, which is great. All right, so now the input, and since we're on output 1 and 2 here, we want to use input 1 and 2 to drive it. Now, If we have them both floating or both to ground, it's not going to move, which currently it's not, so that's good. So let's just hook this to ground, to in1, and then let's get a voltage. We're going to connect this to here. Now if I give this to input 2, it should start turning. So let's take a look. It does. Look at that. And you can see it's rotating this direction here, right? So now if I disconnect the power, if I move the ground to input 2, and then put power on input 1, it should reverse rotation and go the other direction, which it does. Now it's going this direction. Okay, so we now have verified. Let me stop this. So we've now verified that the wiring here, these two outside pins, are in fact the motor drive lines. And at 5 volts, we saw it drives this and runs just fine. In fact, we could go up to 6 because right now we're not driving anything that is only 5 volt. So in fact, let's go up to 6 volts and see what that does for power. In fact, let's run through changing the power on this just so you can see that we can adjust the rotational speed. So let me go back to here and to here. So this is our 5 volt speed here. And I don't think I have an easy way to mark this. If I put a piece of tape or a dot or something on it, it might have made it easier to see what it's doing. I don't have a paint pen or anything. Let me see if I can do this. Well, not super prepared for showing that. So, you'll just, it's not as great as I would like, but you can see that it's rotating. It is. And of course, on my screen, it looks like it's rotating the opposite direction it actually is. It's rotating this way right now. And I'm at 5 volts. So if I decrease the voltage, we could do this via PWM. So I'm going to decrease the voltage to half of that, 2.5. If I decrease to 1, oh, won't even go all the way down to 1. So it looks like it's about as slow as this motor will go. And this is at about 2.5 volts. Any slower, and it just stops. Yeah, so at about 2.2, 2.3 volts, it just quits moving. So this is about the slowest we're going to be able to drive, which seems fine. And this is why this 130 RPM is pretty nice, right? Now, if I increase this, and here's at 6 volts. Let's see if I can do this. Just so that it's a little bit easier to see what it's doing. Let's come. There we go. So there's 3, 4, 5, and 6. So this is 6 volts. This is maximum speed for this motor. All right, I dropped it back down to 5 volts because that's what we're going to use to power all of our stuff. Okay. So now let's wire this up to use a PWM to drive these inputs instead of, just these jumper wires. So now let me see if I've got, I think I should have some wires that we can connect right from this Grove or Quick over to here. So really a Grove to 4-wire female would be perfect. So let me see if I can find one of those. I'll be right back. All right, found one. This should do exactly what we want. So come back here, and already running out of space. I'm just going to put this upside down because it works a little bit better. Yeah, we're going to have to switch. I need USB coming in this side from the PC, so let's see if we can squeeze this all in. Maybe we can go a little higher with the camera, give us a little bit more space. There we go. All right. So I can plug this in here. And we'll take this. You can see ground 3.3 data and clock. So ground. Data, or VCC, data is white. Data is white. And clock is yellow. All right. Okay, so we have that and we'll power this via USB. Now, the one thing that we need to be cognizant of, and this isn't always obvious, but when you're using hardware... Oh, I got a question. Oh my goodness. Hey, Adam. Yeah, so the way that this driver board works, good question. So the driver board basically takes in voltage across the entire range of whatever the motor takes. And I think this is tolerant of, I don't know, something like up to 24 volts. We've only got a 6-volt motor, but the driver can tolerate a lot more. The really nice thing is that you can take this input and give it a PWM instead of just a change in voltage. And we're going to do that from here to basically give the look of an analog through a PWM to the inputs. So if we adjust our PWM inputs, it looks to this, or at least to the motor, as a change in voltage. So these drivers, and they're super cheap. I think I got like 10 of them for $12 or something. They're about $1 a piece, maybe even less. And they handle all of the current flow, right? So you don't have the PWM from the microcontroller trying to drive the motor. It's just driving this driver, and it then figures out which one to go through. And from that PWM signal, the input, it corrects the polarity on the output as well for you. So for, sub $1, you can drive a whole bunch of different motors with them. So that's what we're going to do now, is connect up some PWM here to here. What I was doing, though, is I was talking about, I've got voltage from a bench supply coming in here, and then I'm going to use USB to power this, which then powers this. So I have two totally separate voltage sources between here and here. That's totally legit and legal to do, but they need to have a common ground. Otherwise, you can get some really weird behavior. So I'm just going to common ground these, and that's really easy to do. I'm going to connect the ground from the power supply to the ground of my USB, just like that. So this means that the ground for both is the same, so the potential differences will be from the same reference point, right? I'm sure there's a better electronics way to explain all of that, but really, anytime you have things like this, make sure you've got common ground. Otherwise, you can get some behavior that will be really confusing. And I know this because I've made the mistake before where you don't have a common ground and all of a sudden things are not behaving the way you expect. All right. So now we have that all wired up. The only thing left is to go from the PWM here to our outputs. And so we're going to need two different channels, right? We have two inputs over here. So we're just going to connect up two of the PWMs. I'm trying to see if they're listing them. I'm trying to figure out where number one is, if it's at this end or this end. And it does not say. So I guess we're just going to start all the way down here. And the nice thing is the way these PWMs, this board works, is this center one is a voltage output, and it just takes whatever our voltage input. Get my fat fingers out of the way here. So we have VCC, and this is coming from our 3.3 here. That powers this circuitry, but the voltage that it goes out to the servos comes in on this V+. So we could, in fact, drive our 6 volts in, put 6 volts in here, and we would get the 6 volts out here. In our the device that we build, we will likely do that, but right now we don't need to worry about it. We're going to just use the output here. We don't even need the ground. This is 3-wire for typical servo operation. Let me grab a servo and I'll just show you that because we're going to be using them. So here we go. This is a typical servo. In fact, this may well be the exact ones that we're going to use. Pretty big though, maybe not. But you can see these have 3 wires. The PWM, a ground, and a signal, or not signal, but power. So we've got the PWM signal comes in, and then the power to actually drive the servo. So that's what this is set up to do. All right, so what we need is we just need the PWM output. That's all we need is the signal output from here over to the driver. So let's hook up 2 of those. And I need a different wire, female to male. Just going to start 2 on the farthest left. I don't know exactly where number 1 is on this, but should be easy to test. And then these will come to the inputs 1 and 2 here. If that makes any sense. I know this is starting to get to be a mess of, on the bench, but all right. So quick summary of what's going on. I have power from a bench supply comes in to the inputs on this motor drive. Also is in 1 and in 2 are the PWMs from here. This PWM driver is connected to the I2C bus over here. We have a common ground across. Really, that's it. So now we should be able to drive PWMs here to affect our input, and the duty cycle of that will change the motor speed. So now we can actually get into writing some code. What are we at on the clock? We're about 1 hour in, so we've got plenty of time. I'm gonna, let's say, probably run for another hour or so. We'll see if we can get this motor up and driving, and then call that a win for the day. Okay. We don't need this anymore. All right. A few different ways to look at this. So we have core over here. We could put our PWM driver in it. Let's just start. I'm going to worry about re-architecting that stuff at a later point. The whole idea here is from the desktop, we could actually use an FT232 IO expander, which could be interesting. And then you could actually drive the PWMs from your desktop. In that case, we'd want it in core because we'd be using it from both. But for now, we're just going to do the YoshiPi. See, now I've got myself thinking maybe I should try it with the FT232 because I have one sitting right here on my desk. Let's just continue here. All right, let's add a dependency. And this is a PCA 9685. We come back here and look. It says it right down in here on the silk screen. So we can look for, the nice thing is Meadow Foundation has all of this stuff for us. 9685. And it comes up right there. I probably don't need the beta. Let's just go with 203. And really, I don't think we need anything else. I don't think that there's a driver for the motor driver, the DRV8833, because really it just takes in a couple of PWMs. Might be interesting to create a driver for that, though, to give us rotational direction and speed. Maybe I'll do that after the stream is over. I don't know anybody's all that interested in watching me do a driver development. But let's come in here and let's start with, what do we name this? It's going to be a motor assembly, right? Or a drive assembly. So I'm calling this a motor assembly because it is the entire package, right? It's not just the motor itself. It's going to be the collection of the motor, the PWM generator, and the driver. And in fact, we'll probably have a steerable motor assembly that has the servo involved as well. But we'll worry about architecting all that stuff later. We're going to need a PWM generator. So these are the two that are going to be marked as in here. So our N1 and N2 in this case. So those are the PWMs that are going to drive that. And let's take in this PCA 96. Do we need the 9685? I don't think we do right here. I think all we need are those two. And to start with, I'm just going to put in a run method. We're just going to basically give it some signal and drive it. We'll worry about adding methods for, forward, reverse, and speed once we just verify that we have this thing working, right? And so in order to drive, we know that we want to set one of them. Let's set the duty cycle of it to full on, and the other one full off. So that should give us full speed rotation in one direction, right? And then in theory, that gives us, actually not 0.5, right? This would give us half speed in one direction. Now, just testing it with the bench supply, I know that when we got down around 2.5, it quit moving. So that's not exactly right. So the reality is not exactly the theoretical. So it's not a linear motion relationship, but good enough. So that should give us, man, actually, I think that's everything we need, isn't it? Let's go over here to our app and see what we can do. Move that over to another class so it's out of our way. It's now over here. And back here, we're going to create this PWM generator. So we're just going to use the Grove I²C on this. So basically Grove I²C equates to this hardware Grove I²C. And then we need our address. If we come over here, it's got a bunch of resistors to set the address. And I don't know that it's really obvious here. It's got a bunch of resistors soldered in, so I think that these are all... I honestly don't know if that means they're closed. I think these are all closed, right? It's got a resistor across them. I can't read it, but probably a 0 ohm maybe. Let's see. Whoa. Let's see if I can read those. They say 221, so they're not 0 ohm. Actually, 221 and 103. I don't use this quite often enough to know exactly. So, whatever. We're just going to guess at one. They're either all one direction or all the other direction. So let's just go with, I think, 64. It's always the biggest challenge, is figuring out the address on a new piece of hardware. Taking a look at the back to see if it says what the default is. It does not. I probably have a sample app somewhere that I've used this before that has it, but we'll just, we're going to test it with that and see what happens. So then it's going to want 2 PWM ports. Interesting side note, these pins are called LED because the data sheet for these parts, this 9685, calls it a LED driver. So I think when they initially made it, the idea was it was for generating signals for LEDs, and then somebody realized that they're really good for running servos, so a lot of times you'll see them on these servo boards. Now the frequency here, this is an interesting one. I think that these motors require a fairly high frequency. If it's low frequency PWM, it actually makes an audible noise so as it tries to drive the motor. So you want higher frequency so it's outside of human hearing range. I'm going to go with 10K. I think 10K, it says on the back what it can go up to. Oh, no. 40 to 1,000 hertz. So we're going to go 1,000. So that's for the first one. And the second one will be LED 1. I come back to our motor assembly, and I'm going to initialize, make sure that these are set to duty cycle of 0. So we'll initialize it to stopped. Well, theoretically, that's all we need to make this work. Now I'm going to find my USB cable and power up the YoshiPi. I can't tell if I was on the wrong screen or not. So in summary, just in case I had it on the wrong camera, which I think I did, we're going to create the PWM generator, address 64, at 1 kilohertz for each PWM into the motor assembly, and then tell it to run. We shouldn't need anything else. So really all of this run method is unnecessary for what we're doing, and the display service for running this display we don't need. All right. So we have power here. We have power here. Need to power up this board over here. Okay, everything's powered. Now let's copy our application over. This has some app on here from some test, so I'm just going to remove all of it. And then I'm going to copy the whole output over. Every time I do this, I always say, yeah, I really should get debugging working. And I really should. There is an extension that you can use from Visual Studio to debug to a Raspberry Pi. My experience with it is it doesn't work very well for me, but I know other people have really good luck with it. There is another way to get debugging working, but you have to manually launch some stuff. It's not straightforward. It'd be nice if Microsoft did, actually spend a little bit of resources trying to get all that stuff working. 20 years ago, you could debug to a device real easily, and now it is always a challenge. I should get that working, but for what we're doing today, it's not all that big of a deal. Let's just do .NET and run the app. See how lucky we are on the first run. Oh, and I better. All right. Oh, what is it not liking? Yeah, I kind of knew that was happening and didn't even think about it. Okay, so it's complaining here about not having a digital signal analyzer. This is a type that was added in the latest 2.0 release of the Meadow Stack, and the YoshiPie library has not been updated to target it. So the fact that we have this one, that's our problem. So not exactly what I wanted to be doing right now, but I guess we'll go get this fixed. No time like the present. I'll bring this over. All right, so we need to update the references for this. It's another thing that I really wish Microsoft would fix is the ability to change between, you know, on a configuration, change between project and NuGet references. Because I do this all the time, and I can't imagine that I'm the only developer that does stuff like this. Let's see, we want, I don't think we need beta versions, so we'll do that and that. So you can see here, this gives us the latest version, and here would give us the latest, including betas. So if I change that and save it, and that changed our packages here, and it's targeting 2. Make sure everything's clean. All right. All right, so now I need to push a new version of this. Let me go see what the latest is that's out there. One 1.2.1. Right now I'm just looking at the old releases. In fact, I guess I could bring this over in case anybody wants to see what I'm doing. So I'm looking at what I have set up. So this is the last release here, 121. Off of main, so I really need to stash what I've got. Really, it's no different. So if I come back to main, yeah, I know it already exists. I really need to get a whole bunch of this stuff fixed. I think, though, I can just change our version number to 1.3. Check that in. So let's just do that. I'm just going to do this right on the main branch. So do as I say, not as I do. Make this 1.3. There are no other changes. It's another one of those things that you would think that I shouldn't have to do this because I'm referencing, you know, the latest, that it would figure out how to update that. But the package manager for .NET is a little bit strange in my mind. Okay, so we have this. Add that, push it. And then nicely, I can do this and call this v1.3 and push this tag. So that tags it here. And we come over to the repository and look at this. Of course, it's going to make a liar out of me. It should have automatically started an action. When I pushed that tag. Well, it should have just done this for me when I tagged it, but evidently it doesn't want to do that. So we'll go create a release. All right, so what this is going to do is this is going to build it and publish it to NuGet for us. I should have done this earlier in the week when we did the Meadow 2.0 release, but I'll go over to Discord, see if we've got any questions. Also in the chat. Yep, I don't see anything. Okay, so it should have published it. And in fact, we should be able to go out and verify that if we want. Why does it not have 1.3 here? One 1.3 was pushed. There it is. Okay, so it's there. It hasn't yet been indexed, but if we reference it by number, it should be fine. Okay. What were we working on? Back to here. One 1.3. So it sees it as 130. Let's do a rebuild of the whole thing. Not core. Let's build the whole thing. Got wildly off track there. All right. What has changed? It is just these. And back to here. Now it can't find Meadow 2.0. All right. I'm just going to try to push everything. Rebuild the whole thing. Feels like it's still not pulling over all the right Meadow stuff. You got the right stuff. All right. System I/O ports. I bet. All right. It's missing version 9 of System I/O ports. Thing is, I don't know who's pulling it in, right? My guess is here. There it is, right there. So this is built against 9, and I only have .NET 8 installed. Let's just change this and see what happens. I'm trying to avoid going in and building all of the Meadow stack with this. So let's come here. We're going to change this to a 9. See if that works. I don't think that's going to fix it. Oh, there are a couple of things that bring it in, that's why. We're not even using the serial port, but we have to deal with all of this. Let's see if that's enough to fix it. Nope. is all the Android stuff. Yeah, there it is right there. Same binary. I think that's the right property, isn't it? I think this is the one I want. Right now I'm trying to get it to pull in the system IO ports 9.0 to our output. Right now it's pushing that 8.0. I'm almost certain of it. See if we look at this. It says that's file version 9, but it can't find it. Oh, what are you doing, Microsoft? Right now I'm trying to figure out what the fastest way forward was. I was going to go to the FT232, but then I just remembered that it only has a single I2C bus on it, so that doesn't get us where we... I guess a single I2C bus can do... frustrating when things like this happen. So I've got a couple of options here. I could install .NET 9 onto this Raspberry Pi. I could bring in all of the Meadow projects as project references, or I could move to the FT232 and try to use it direct from the desktop instead of using the YoshiPi to start with. There are pluses and minuses of all of those options. Let's just install .NET 9 over here. See if that fixes it. I've got a gist somewhere for this. Actually, I wonder if it's already on this device. Nope. That's the problem, is I don't think that they've got an official 9 version. So you can see right here that this is just using the .NET install. And that immediately tried to pull 804, .NET SDK 8. Why it's not pulling 9, I don't know. 9's been out for a little while. You'd think that they would have updated that. See if apt will bring it in for us. I understand why this is happening. It shouldn't be it's not a preview. Let's see if this does it. And if this doesn't work, then I'll have to go some other route to attack this. Yeah, can't find that either. All right. Okay. One more try, and then we'll hang it up for the day, and I'll fix this offline. All right, we'll see if this works. If it doesn't, I will fix all of this offline. Still trying to find ports 9. Oh, who is bringing that in? Oh, so frustrating. That's 8. That's 8. Well, it looks like I am stuck. It's going to take a bit of time to grind through figuring out why this is behaving the way it is. So I will fix this and get it all pushed. But I am done for today for streaming. Hopefully somebody found this useful. Didn't appear to get a whole lot done, but we did not achieve our goal for the day. So it goes. That's the nature of development. Sometimes development's hard. At any rate, I will try to be back again next week, about the same time, Saturday morning, 9-ish Central Time, whatever that turns out to be in your time zone. Thanks for watching, and if you have any questions, join us on Discord. Leave comments down below if this is the edited recording, that kind of thing. Again, thanks for watching.